Hey all, in this video I'm going to run through the basics of solving acid-base titration problems where we have a weak acid with a strong base, or alternatively a weak base with a strong acid. So there are really two parts to solving these problems. The first thing you need to do is to calculate the moles of acid and base that you're combining and decide if you are before or at or after the equivalence point. Now obviously you don't need to do this for the initial pH because you know that you are before the equivalence point if you haven't added anything from your burette yet. So you calculate those initial numbers of moles of acid and base, and then that will inform you what type of equilibrium calculation you need to do. So obviously if nothing has been added from the burette, then you're just going to do a Ka or a Kb ice table just like you normally would for a weak acid or a weak base. If you're before the equivalence point, that is that you haven't added as many moles from the burette as what's in your container, then you'll be doing a buffer calculation, and if you're lucky, you'll be at that half equivalence point where you have equal moles of acid and base, and then the pH is just equal to the pKa. If you are at or beyond the equivalence point, you'll do a Ka or a Kb ice table depending on the exact nature of your titration, but you'll have to account for the dilution because you've added a bunch of stuff from the burette. So that's kind of tricky. So in this first example here, I'm going to look at the titration of the weak base ammonia with the strong acid hydrochloric acid. And so for the initial pH, I'm just going to do a Kb ice table because I've just got a solution of a weak base that I've added nothing to. So I've got my base, which is ammonia, water, that's pure liquid, in equilibrium with the conjugate acid of that base and hydroxide ion. So they give me my initial concentration here is 0.2, the water is irrelevant, that's 0, and we all kind of know how this is going to go, right? That's going to go down by x, that is irrelevant, that will go up by x, that will go up by x, and then when we get to equilibrium this will be 0.2 minus x, and that will be x and x. So my Kb is going to be equal to x squared over 0.2 minus x, which is equal to 1.8 by 10 to the minus 5. So what do we know about x? Well, x has got to be somewhere between 0 and at most 0.2. So I'm going to go ahead and put that into my solver, and I'm going to get x, which will be equal to my hydroxide ion concentration because I'm doing a Kb ice table. Okay, so I have to go out of the full screen mode to pop my calculator up. It's kind of annoying. So turn my calculator on. It's like I already set it up. Okay, so what we've got x squared divided by 0.2 minus x, and then that is equal to 1.8 by 10 to the minus 5. And then now we're going to set our range. Our lower bound is 0, and our upper one is going to be 0.2. Okay, so my guess of x, I'm just going to put it in the middle, 0.1, and now I'm going to solve, and there's my x. I'm going to quit out of there. X is 1.888 by 10 to the minus 3. 1.888 by 10 to the minus 3 molar. And so from here, what I'm going to do is if I do 14 minus the pOH, that will give me the pH, and so that would be 14 minus the negative log of the OH, or the negative log of my X. So I'm going to do 14 minus negative log of X, and it should be basic, right? So it ends up being 11.3. Okay, so thinking about our problem, Let me get rid of this piece of paper, I don't know why that's there. Thinking about our problem, what we're going to do now is we're going to add acid as we go through here. Okay, so if this was 11.3, then as I add acid, the pH should go down. So I want to be mindful that as I add more and more acid, the pH should be getting lower and lower, and if it's not, then I'd go back and check my calculations. So the next point that I'm going to look at, and I'm just going to pick kind of one at random, is, let's do this one here, C, sorry. So after 10 mils of 0.5 molar HCl. So remember, my first step is that I've got to calculate the number of moles of acid and base that I'm combining. So 10 mils of 0.5 molar HCl. Would have been easier just to use the eraser, wouldn't it? There we go. Okay. So we have 10 mils and our concentration is 0.5 mole for every 1 liter. So I'm not going to do it in my head because I don't want to make a mistake, right? But basically we know that we're just going to be dividing that by 100, aren't we? So 0.005. So that's how many moles of my strong acid. And then for my base, 40 mils, and it is 0.2 mole for every 1000 mils. So 40 times 0.2 on 1000, and that is 0.008 moles of ammonia. So we know that we're before the equivalence point because we haven't added equal amount of moles of acid as what base we had. So the I should say that these are moles, not molar. So what we want to do now is we want to figure out how much acid and base we're going to have once these two have been combined, and then we can do our equilibrium calculation, which we know in this case is going to be a Henderson-Hasselbalch buffer type calculation because we are before the equivalence point. So what's going to happen is that these guys are going to react like so, and I'm going to have 0.005 of that reacting with 0.008 of that. That originally will be 0. This is irrelevant, so this is going to get all used up. Only some of this will get used up, and that will make some of the conjugate acid. So I'll have no strong acid left. I'll have 0.003 moles of ammonia left, and I will have 0.005 moles of ammonium. So now I can do my, so this is my conjugate acid, and that's my base. So now I'm ready to go ahead and do Henderson-Hasselbalch. pH equals pKa plus log of moles of base over moles of acid. And we'll know if we've got it around the wrong way or not, or anything incorrect, because it won't be less than 11.3. So we're going to want the pKa there. So what we have at the moment is we have Kb, don't we? So what I know is that Ka is equal to Kw on Kb, and then pKa is the negative log of Ka. So my pH here is going to be the negative log of Kw 1 by 10 to the minus 14 over my KB 1.8 by 10 to the minus 5 plus the log of the moles of base, which is my ammonia that is unreacted, over the moles of its conjugate acid, which is equal to that. So when I put all of this into my calculator, let's see what we get. Okay, so negative log 1 by 10 to the minus 14 over 1.8 by 10 to the minus 5 plus log 0.003 on 0.005, and fingers crossed it's less than 11.3. So I got 9.03. So going in the right direction, okay, heading in the right direction. So just explaining what we did. The initial conditions, we just did a KB. This guy, we did our little bit of math and we figured out that we were before the equivalence point. And we know that we were before the equivalence point because we didn't add an equal number of moles of acid as the moles of base that was originally present. So once we'd figured that out, we then went ahead and figured out how much of our weak base that was unreacted we had and how much of its conjugate acid had been produced. And once we got those two numbers, we put those into Henderson-Hasselbalch and we get the new pH, and then we checked that our titration was heading in the right direction. So again, it's kind of doable, but it's not, you know, trivial. I'm doing a better job here of getting rid of this stuff, aren't I? Okay, so let's do one now where we're beyond the equivalence point. So I'm going to just assume that the very last one in the list here is beyond the equivalence point, and we'll see if that works out. So again, our first step is calculate the moles of acid and base that are combined. Okay, so we got 20 mils of the acid and its concentration is 0.5 mole for every 1000 milliliters. So again, I try to avoid doing mental arithmetic just in case I make a mistake. And there we are, 0.01 moles of acid was added. Okay, and now the amount of base that we had originally isn't going to change, is it? Right? That's going to be the same for all of them, so you don't necessarily need to keep calculating that. So we had 40 mils and it was 0.2 moles per 1000 mil, and we'd already calculated that, as I said. So 0.008 moles of ammonia. So you can see that we're a little bit past the equivalence point. Okay, we've added more moles of acid from the burette than the moles of base that were in the flask. So let's figure out how much we've got here. The first thing to note is that we're going to have 60 mils total volume. So we need to know that because we are at or beyond the equivalence point, we're going to have to account for dilution. So I combine HCl and ammonia, and that's going to make the ammonium cation and the chloride anion. And I had 0.01 of that, 0.008 of that, none of that, and none of that to begin with. Now the chloride is irrelevant, it doesn't affect the pH because it's derived from the strong acid HCl. So this is not going to be the limiting reactant. The ammonia will be the limiting reactant in this case. And so we're going to be left with 0.002 moles of HCl, no ammonia, and 0.008 moles of the ammonium cation. So when you are beyond the equivalence point, what you really got is a solution of your conjugate acid and a little bit of excess strong acid, right? And what we're going to do here, because we're dealing with the pH of a solution that contains a weak acid, is we're going to do a Ka ice table, but we must correct for the dilution. Okay, so that's going to be a little bit tricky. So the concentration of our strong acid in this case is going to be 0.002 moles in 60 mils. That'll be that. And then the concentration of our weak acid will be 0.008 moles, and that's also in the 60 mils. So there we go. So let's go ahead and figure those guys out. 0.002 divide 0.06, and that's that. 0.033. You can make a note that that's recurring. And then 0.008 also in 0.06, going to be 4 times that, isn't it? Right? So that ends up being 0.133 recurring. Okay, so now, because we're trying to figure out the pH of our weak acid solution, we're going to do a Ka ice table, which is always a little easier to set up without making a mistake. And our initial amounts are, we're going to have 0.133 moles per litre of that, 0 of that, and then 0.033 moles per litre of that. So how is it going to change? Well, this is going to go down, this is going to go up, and this is going to go up. So when this all comes to equilibrium, that will be 0.133 minus x, that will be x, and that will be 0.033 plus x. So the x here represents the little bit of extra H plus that is formed by the dissociation of the ammonium ion. So it's not going to be much, it's going to be pretty small, because the Ka for the ammonium ion is going to be Kw on Kb. So that will be 1 by 10 to the minus 14 over 1.8 by 10 to the minus 5. And you're going to see that this is a really tiny number. It's like 5 by 10 to the minus 10. Well, we'll do the math rather than. There you go. It's at 5.5556 by 10 to the minus 10. So that x is going to be itty bitty, all right? That x is going to be itty bitty. There's a reasonable chance that that x is so small that it's irrelevant. So if we were to calculate the pH here, just ignoring x, we would just do that the pH equals negative log of 0.033. So let's see what we get when we do that. Negative log 0.033. We can put a couple of 3's there because we knew that that was recurring. And there's our pH, 1.48. Now we can solve it completely. So we know that Ka will be 0.033 plus x times by x over 0.133 minus x, and then that is equal to 5.56 by 10 to the minus 10. Now our value of x has to be somewhere between 0 and 0.133. Okay, so somewhere in there. So let's set this up. Try and move this over so you can see it all. Math up. Solver. Clear that off. 0.033 plus x multiplied by x divide 0.133 minus x is equal to 5.56 by 10 to the negative 10. And then our x, remember we got to set the range. We want it to be between 0 and 0.133. So I'm just going to put this in here to begin with as 0.07. That's pretty close to halfway between the endpoints of my range. And now I'm going to solve. And there's my answer. And remember what I said? My expectation was that x was going to be tiny. So my x here is really tiny, 10 to the minus 9. So my actual pH should be negative log of 0.033 plus x. Right? Should be that. But I don't think that's going to be a lot different than 1.48. So we're going to do negative log of 0.033 plus x. Pretty confident it's going to come out, there you go, 1.48. So, you know, it didn't really make a big difference. So if you're a little rushed and you have the awareness that your x there is going to be really tiny, you can kind of like just, if you feel confident, you can ignore it and just give the approximate answer, and you're probably going to be close. So we saw kind of all three types of problems here. We got what we were expecting, which was the pH was just going to kind of continue to decrease as we go down. We started at 11.3 and then it went all the way down to 1.5, so that's good. Before we added any acid from the burette, we just knew that we needed to do just a straight up regular KB ice table. Once we started adding acid from the burette, we always calculated the moles of acid and the moles of base that we were combining to figure out how much of each component we had after that combination. Where we found that we were before the equivalence point, we did a Henderson-Hasselbalch calculation, and when we found that we were either at or after the equivalence point, we did a more complicated calculation, which was that we did a Ka calculation, but we had to account for the dilution. So it's pretty complicated. I'll do one where we've got a weak acid in our vessel underneath our burette, and that we're adding a strong base to it, just to show you how you kind of do it the other way around. This problem is also a little bit different in that they give you a pKa rather than a Ka. So we're reacting, looks like we're adding what's called propanoic acid with sodium hydroxide, and we recognize this as being a weak acid because we've got that ending that is classic for indicating that we have a carboxylic acid, which are all weak. All right, so initially we just got to do a Ka ice table for that guy. So I'm just going to call it HA is in equilibrium with H plus and A minus. And my initial concentration is 0.25, that is 0, that is 0. We know where this is going to go, that's going to go that way, plus x, and then when we're at equilibrium, we will have 0.25 minus x, x, and x. The only thing that's different here is that they've given you pKa rather than Ka, and all we have to remember is 10 to the negative pKa equals the Ka. So my Ka in this case is going to be equal to x squared over 0.25 minus x, and that will be equal to 10 to the negative 4.89. My value for x is going to need to be somewhere between 0 and 0.25. Okay, so let's put all of that in. Math, up one, solver, clear it off. X squared divide 0.25 minus x, close, is equal to 10 to the power of negative 4.89. 9. Better delete all that other stuff. Okay, good. I'm going to put my range in. 0 to 0.25. And then let's just put this 1.125. Okay, so that's that. Let's go ahead and solve it. And it worked. So we'll quit out of here. And there's my value for x. Now x in this case is equal to my hydrogen ion concentration. So negative log of x will give me my pH. So negative log x and 2.75. Okay, it's acidic, right? So it's a weak acid solution, so that's exactly what we would expect. So everything looks good. As we add the base, all right, as we add the base, we're expecting that the pH is going to go up. So whatever values we get from here should be bigger than 2.75. Okay. I'm getting better at doing this. So I'm just going to assume that for B, we're before the equivalence point. I think we probably are. Yeah, we definitely are. Okay, so the first thing I got to do is figure out how much of each of the components I'm combining. So we've got 2 mils of the base, and the concentration is 0.33 mole for every 1 liter. There we go. Okay, so 2 times 0.33 on 1,000. 6.6 by 10 to the minus 4 moles of NaOH. Now we're going to calculate our amount of acid, and like I said, that's not going to change, so you don't have to keep calculating this throughout. We've got 25 mils of that, and it is 0.25 moles for every liter. So 25 times 0.25 on 1,000. There we go. And so then that ends up being 0.0625 mole of our acid. I'm just going to call that HA for weak acid. All right, so let's make this clear. We got our weak acid reacting with the hydroxide ion, and that's going to give water and our conjugate base. So I got 0.0625 of that, and then I've got 0.00066 of that. That's irrelevant, and I've got none of that. So hopefully you can see that we are definitely before the equivalence point. I haven't added equal number of moles of base from the burette. So this is going to go down because it's the limiting reactant. This is going to get entirely, it's the excess reactant, sorry. The base is going to get entirely used up, and then we're going to form our conjugate base. There we go. So everything's like so. So this just goes down to 0. This goes to the original number of moles of the base, and then we have to do some math here. So 0.00625 minus 6.6 by 10 to the minus 4, keeping it simple, 0.00559. Okay, so as long as we didn't kind of like copy anything over incorrectly, we should be good. Yeah, that's that, that's that. Okay, so what have we got? We got a weak acid in equilibrium with its conjugate base. So we are before the equivalence point, so we're going to do Henderson-Hasselbalch. So pH equals pKa plus log the moles of base over the moles of acid. Now I like these because they're just really simple. Now the cool thing about this one is that we were given the pKa, so we don't have to mess around so much. There it is there, 4.89. So that's nice too. Well, I kind of threw you a bone there. 4.89 plus log. And just don't confuse what is the base and what is the acid. The base is 0.0066 moles and the acid is 0.00559 moles. And that's it. We just got to calculate that, and we want it to be that the pH is increasing from our initial pH, right? So 4.89 plus log 0.00066 divide 0.00559. There we go. Boom. 3.96. So we are going in the right direction, okay? We're going in the right direction. So 3.96. And if I was working through all of these, I would expect it, to continue to increase. Okay, so before the equivalence point, let's assume that the very last part of this problem will have us be at or after the equivalence point, and we'll jump to there. So we're going to go to D now. We're going to add 20 mils of our sodium hydroxide solution. So the first thing, of course, calculate the moles of acid and base that you've combined, and then that'll let us know where we are, whether we are before or after the equivalence point. So in this case, 20 mils of base, concentration 0.33 moles per 1000 milliliters. And that'll give me my moles of the sodium hydroxide, right? Okay, 20 times 0.33 on 1000. Here we are, 0.0. Hey, it's 10 times what we had before. Who'd have thunk it? We should have put a little effort in there, shouldn't we? Right? And calculate our moles of acid. Again, it's not going to change. You really don't need to keep doing this. I'm just kind of like doing it to labor the point. It's going to be exactly the same as what we got before, of course. There we go, exactly the same as what we got before. So you can see that we are a tiny little bit, just a tiny little bit past the equivalence point, right? We can see that we've just got a little bit more base added than acid that we started the titration with. So let's figure out what we've got from each component. So 0.00625, 0.0066, 0, we don't have to worry about that. So obviously my acid is my limiting component here. So all of my acid gets used up and gets turned into its conjugate base, and then I have a little bit of extra strong base left over. 0.0066 minus 0.00625. Now I think we all know what this is going to be, but we're just being super cautious to not make a mistake. Okay, so what we have now is a solution of a weak base with a little bit of strong base in it. Okay, so how do we figure out the pH of a weak base? We have to do a KB ice table, but in our case we've got to be mindful to correct for the dilution. All right, so we have a total volume here of 45 mils, and we always have to correct for dilution when we are at or beyond the equivalence point. So let's figure out our concentration of our A minus. So we've got 0.00625 moles, and that is in the volume of 45 by 10 to the minus 3 liters. So 0.00625 divide 45 mils. Okay. 0.1389 moles per litre. It's quite concentrated, isn't it? And then we're going to figure out the concentration of our hydroxide ion. And so we've got 0.00035 in the same volume. Okay. There we go. And so then that is 0.0778 moles per litre. So we're going to do a KB ice table. So we know that we've got A minus plus water is in equilibrium with its conjugate acid and hydroxide ion. So this initially 0.1389, that's irrelevant, that's 0, and that is 0.0778. This will go down by x, that remains irrelevant. This will go up by x, and this will go up by x. So once we get to the end, we'll have x of that, and we'll have 0.0078 plus x hydroxide. So how are we going to figure out what the hydroxide is? Well, first of all, we've got the pKa, which is equal to, I'm jumping ahead a step there, 4.89. So therefore our Ka is equal to 10 to the negative 4.89. So we know that Kb, which is what we're interested in, is Kw on Ka. So that's going to be 1 by 10 to the minus 14 on 10 to the negative 4.89. So go ahead and do that math. 1 by 10 to the minus 14 divided by 10 to the power of minus 4.89. Hit enter, and it's an itty bitty number. A bit bigger than what we had before for the Ka of the ammonium ion, but it's still pretty small, right? 10 to the negative 10 again. So there's a fair chance that that x is so tiny as to be irrelevant. So let's go ahead and figure out the pH if that was the case. The pOH is equal to the negative log of the hydroxide ion. And I'm saying, what about if we just assume that x was basically 0, then that would be negative log of 0.0078. We go, and then that would be 1.09. That's the pOH, and then the pH is 14 minus the pOH. 14 minus that answer. And there we are, 12.8 or 12.9. Okay, well now let's do it all sort of completely. Kb will be equal to x lots of 0.0778 plus x over 0.1389 minus x, just using the bottom line of my ice table there, and then that is equal to 7.76 by 10 to the minus 10. So let's do that. Math, up 1, enter. Let's clear that off. X times by 0.0778 minus X divided by 0.1389. Almost made a deadly mistake there. There we go. Just averted disaster. Okay, that looks good. And then that's going to be 7.76 minus 10 to the negative 10. Better delete the rest of it. Oh. Let's get this right. What a mess, huh? There we go. Minus 10. Okay, took a while. Okay, so setting our bounds here. Lower one is always 0, and in this case, X, it's got to be between 0 and 0.1389, so that bottom term doesn't become 0. There we go. Okay, and I'm just going to put this in as 0.07 because that's about in the middle of that range. I'm going to solve it. Ooh, we got an answer. And so our X, as anticipated, was itty bitty yet again, right? So my hydroxide ion concentration, there it is, 0.00778 plus my X, okay, and so then my POH is going to be the negative log of that, and then my pH will be equal to 14 minus the POH, which is equal to 14 plus the log of 0.00778 plus X. So my pH is equal to 14 plus the log of 0.00778 plus X. Now, you think it's going to be a lot different from what we got before? Let's see what we get. Equals 11.89. When we did it before, we got 12.89. What have I done here? Anything wrong? Oh, I put an extra 0 in. I picked up an extra 0. There we go. Always worth checking. Let's do that again. 14 plus log of 0.0778 plus X. There we go. Boom. 12.89. Excellent. All right. So just inserted an extra 0. All right, that was it. Okay, so I know there's a lot going on there. Run through this again. First thing we do, calculate the moles of the acid and the moles of the base that we're combining and decide whether we are before or at or after the equivalence point. If we're before the equivalence point, we're going to do Henderson-Hasselbalch. If we are at or after the equivalence point, we're going to do an ice table taking into account the dilution. So that's really it, all right? Now, there are a couple of things to keep in mind. If we're at the initial conditions, it's not really a titration problem. That's just a weak acid or weak base ice table problem. And if we're lucky and we're halfway to equivalence, then we can just use the relationship that pH equals pKa at half equivalence. So there's a couple of little caveats in there. Anyway, these take time to get good at, and you kind of like it's important to kind of show your work clearly because the chance of getting them wrong is modestly high. All right, I hope that was helpful despite my kind of fumbling, and yeah, good luck with everything.